What is adiabatic quantum computing's core principle? Imagine trying to solve a complex puzzle by slowly guiding a ball through a maze without letting it jump or fall into the wrong hole. That's a bit like how adiabatic quantum computing works. It's based on a key idea from quantum physics called the quantum adiabatic theorem. This theorem says that if you prepare a quantum system in its lowest energy state, called the ground state, and change its conditions slowly enough, it will stay in that lowest energy state throughout the process. In adiabatic quantum computing, you start with a simple Hamiltonian, which is just a fancy way of describing the energy landscape of the system. This initial Hamiltonian is easy to set up and understand. Then, over time, you gradually change this Hamiltonian into a more complex one that encodes the problem you want to solve. The goal is to do this slowly enough so the system remains in its ground state the entire time. When the process ends, the system's lowest energy state contains the solution to your problem. This process involves three main steps. First, you prepare the quantum system in the ground state of the initial Hamiltonian. Next, you slowly evolve the Hamiltonian from the starting point to the final one that represents your problem. Finally, you measure the system at the end, and because it stayed in the ground state, the measurement reveals the answer you're looking for. A big factor in how well this works is the spectral gap, which is the energy difference between the ground state and the first excited state during the evolution. If this gap is large, you can change the Hamiltonian faster. If it's small, you need to go very slowly to keep the system in the ground state. Compared to other types of quantum computing that use discrete gates to manipulate qubits, adiabatic quantum computing uses a continuous, gentle change of the system's energy landscape. This makes it especially good for solving optimization problems, where you want to find the lowest point in a complex landscape. These problems are common in fields like logistics, finance, and machine learning. Practically, companies like D-Wave have built quantum annealers that use superconducting qubits to perform these adiabatic processes. They are known for being more resistant to certain types of noise and errors because they focus on maintaining the system's lowest energy state rather than executing precise gate operations. In essence, the core idea of adiabatic quantum computing is to slowly guide a quantum system from a simple starting point to a complex solution, making sure it stays in its lowest energy state the whole time. This approach uses the principles of quantum physics to solve problems by energy minimization, offering a different way to harness the power of quantum mechanics for real-world applications.